This is problem 2-62, it's on page 52. For weight W equal 800 newtons, P, weight also 200 newtons, and distance D equals 60 millimeters, determine the value of H, the height, consistent with equilibrium. So what they've done is they've given us a system here where we've got a tie down to ground that has a rope tied off, a pulley with the first weight hanging off of it, and that weight was the 800 Newton load. And then we've got another rope, comes around another pulley, I guess we'll wrap it straight down then, with a second weight, P, and that weight, no, I've got it backwards, don't I? This is P, and this is W. And so P was the, what, 200 Newton?
Yeah.
Load. And then the horizontal distance, D, is here, and they said, well, it's also here. And that's not just floating out in space. Let's put some support on it, something like that, if you get enough. I know they drew it differently in the image, it doesn't matter. So D is 0.6 meters, or 600 millimeters, take your pick. I didn't feel like writing two more zeros. Well, I guess one more. The height that we're supposed to find, H, is right there. And really it's to the center of the pulleys. No, it's not. I'm wrong. It's to the point where the rope touches the pulley. There we go. So what height? Well, how are we going to figure out that required height? Well, let's think about what would happen. The larger the height, what's that going to do? Well, let's think about the tension in the rope. The tension in this section of the rope is 800 newtons. What's the tension over here? How hard would you have to pull on this rope to keep that 800 newton force from pulling it down? 800 newtons. What about over here? Oh, that seems a little bit more difficult, doesn't it? Here's the thing about a rope. The rope is going to have the same tension throughout. It doesn't matter where it's at. You're going to have 800 newtons of tension. Okay? So, in essence, what that means is there's a tension force of 800 newtons in the entire rope. Okay? Now, in order to figure out the height, let's see, the larger the height, the more that force from the rope is going to change its angle, and the more vertical component of force will be applied to this pulley from both ropes. Well, we only need so much vertical force from each of these to counterbalance that 200 Newton force. As a matter of fact, each one of these ropes would have to contribute 100 newtons of vertical force in order to support the weight. Now, let me say it to you another way. Let's take a free body diagram, and you'll get used to seeing this. FBD, free body diagram. Let's take a free body diagram of the pulley and weight in the center. What forces act on it? Well, there's the 200 Newton gravitational force, obviously. There's also a tension from one rope and a tension from the other. We already know, though, that this tension is 800 newtons in both cases. It has to be. That's just the nature of the rope. Okay? The only real question is, how much angle do we need? In other words, what height do we need? So that the vertical component of this 800 Newton force and this 800 Newton force will counterbalance that 200 Newton force. In other words, summing forces in the y direction, we better get to 0. Now we can already see that it's trivial to say the sum of the forces in the horizontal direction equals 0. Well, that's just, what, 800 times, I don't know, let's call the angle alpha if you like, I don't care. It'll make life easy. 800 multiplied by, let's see, on this side we'll have cosine of alpha minus 800 cosine of alpha. Obviously the two angles are the same because the dimensions d are the same. So those two are going to cancel out, and whatever alpha is, it doesn't really matter. But in the vertical direction, what are the forces? Well, there we've got 800 times sine of alpha plus 800 sine of alpha minus 200 newtons equals 0. Because our free body diagram only has two components of vertical from the tension and one negative vertical component from the 200 Newton force. Now I don't really like using alpha because remember we can deal with distances or we can deal with angles. In this case we've already got a distance, so why don't we use it instead? For example, I see a triangle here. Let me show it to you. This triangle is a right triangle. It has base length 0.6 meters, height h, and of course this side, if we really need it, would be root h squared plus 0.6 squared, right? So let's just use that triangle. In particular, what I mean is, let's see, we may or may not like this. I may be sorry I did it this way, but I'm going to do it anyway. So instead of sine of alpha, what I'm going to do is use, well, I don't know, I'll put another 0 on the end. 0 equals 800 sine of alpha. Well, where's alpha? Alpha's right here, isn't it? So sine would be h divided by root h squared plus 0.6 squared. Right? That's that first term. Plus another 800 h root h squared plus 0.6 squared. Now notice I'm being sloppy with my units a little bit, aren't I? But notice that h and this term will both have units of meters, so they will cancel. Okay? But then the last thing is minus 200. So in other words, I can say 200 equals, well, let's put the two terms together, 1600 h over root h squared plus 0.6 squared. Okay? Now we can put all the constants together if we like, I suppose. This is same thing as 2 over 16, which is an eighth. Right? Because 200 over 1600 would be just 1 over 8. And then solve for h, I guess. So let's see. How do I want to do this? Root h squared plus 0.6 squared divided by 8 equals h. If we square both sides, we'll have h squared plus 0.6 squared over 64 equals h squared. Okay. Get h by itself, or h squared by itself, and we'd have, let's see, probably easiest, h squared plus 0.6 squared equals 64 h squared. And so we'd have 0.6 squared equals 63 h squared. So we take the square root of both sides, or better yet, let's move the 63 to the other side. There we go. Then h would be equal to the square root of, well, let's just do it this way. Let's say 0.6 square root 1 over 63. Okay? So grab your calculators, please, and take, well, I guess the easier way is to say root 63, there we go. 0.6 divided by root 63. Now we got to be careful because this 0.6 has units and they are meters. Let's not forget that. We go all the way back to here, you see that this was 0.6 meters. So what is h equal to? Calculator.
0.76.
How much?
I got 0.076.
Anybody else get the same thing? Seems reasonable to me. So, 76 millimeters. Just move the decimal place over 3. You got millimeters instead of meters. Okay. Any questions about all this? What was the key to it? Realizing that the sum of the forces in the vertical direction have to be 0 on an appropriate free body, and also knowing that the tension in the entire rope is 800. You probably believed me when I eliminate all of this and said I got to pull on this rope with 800 newtons of force, but you might not have believed me if I said I've got to pull on this one with 800 newtons of force, because you see another weight there, you see. But that is the case. Any questions? Yes?
How did you cancel out h there by the bottom right?
Here? Or down here? What do you mean?
To get it over to one side?
Here?
Yes, so sort of that little L of h squared plus 0.6 squared equals 64h squared to the,
Is it here?
yes,
I just subtracted h squared from both sides. There's 64 of them on that side and one on this side, so I just took one away from both sides.
oh, okay.
Don't let the fact that it's h squared confuse you. It's a good question. Anything else? Yes.
I was confused from the beginning. I was confused on what fx and fy, what you were trying to get with those, and then I didn't really understand.
Fx and Fy, I mean, sum of forces in the horizontal vertical direction. It might have helped if I had drawn a coordinate system. Does that help a little bit?
Yeah.
So what I'm saying here is I'll sum all the forces in the horizontal direction on this free body diagram. Well, there's a component, Tx right there, and another component, Tx right there, and they cancel each other out. That's why this equation said, yeah, it's not really all that interesting. There's nothing that's unknown there, right? Okay. Because basically all we said was cosine of alpha equals cosine of alpha. We already knew alpha was equal, right? Because the thing's symmetrical. But summing forces in the vertical direction was a little bit more interesting because there's a, let me get rid of this bit. There's a vertical component, Ty, on each side. Tension from each rope contributes to the vertical force on the weight. That's why there are two of them here. This is Ty and that's Ty. And then that's why there was negative 200 newtons pulling the weight down, you see.
Yeah.
So the free body I took was that center section of the image, right? I basically just extracted this bit right here, called that my free body diagram. Okay. Anything else? These are good questions. If you're still confused, let's continue with the discussion.
I was just trying to connect that, and then after that I have more questions.
Sure. Well, what I did then was once I had this equation, and I knew the sum was 0, then I just started putting it all together. Sine of alpha, that might be part of the question about the geometry. What I did then is I recognized this triangle, and that might be confusing because maybe I should have said I recognized this triangle instead. But h is still the vertical component, right? And the horizontal component is still 0.6 meters.
How did you know that y was 800 on both sides?
It's not. It's 800 times sine of alpha.
Okay.
So this whole thing is Ty.
Okay. Then what's the other 800 sine alpha?
Right over here. There's two of them. There's tension on either side
How do you know it's 800 on the left?
because it's a rope. And so the tension in the entire rope will be 800 newtons. It's one of the reasons for selecting this problem because that's not something that's explicitly stated, I think, usually.
So with that whole progression over to the left,
Sure.
it has both newtons and meters.
Right.
And so I'm just sort of tracking down
The
that
units.
800.
So one of them is the length of this side. It has units of meters. The other is the length of this side, this h. It has units of meters. And then finally, there's this horizontal piece which has units of meters. So this is height in meters and hypotenuse in meters, so they cancel. So where did they come back in? Well, if I solve for h itself, h still has units of meters, doesn't it?
Well, I'm wondering where the newtons get canceled out because isn't it 800 newtons there?
Oh, right here.
Oh, okay.
Yep. Good question. What else? You guys look like you've been just run over by a truck or something. You okay? All right. Anything else? Oh, it was a bus? Okay.